We'll be talking about information lattice learning, which is a new approach, a fairly new approach to the AI that we've been developing, and it has all kinds of downstream applications, whether it's in knowledge discovery, creativity, semantic compression for 5G and 6G, classification, etc. Um, and it actually goes back to Claude Shannon's 1950 lattice theory of information. And so, yeah, I was thinking maybe I'll cast the talk a little bit as a node to Shannon, given that he's arguably Bell Labs' greatest son. So uh, yeah, but yeah, and over the summer I actually went to northern Michigan, Claude Shannon's birthplace. So I went to Gaylord, Michigan, which is right here. It was actually super interesting. Like yeah, the barn and so on are still around, kind of, and so on. So you can kind of see them. Um, yeah, this part of the country is super beautiful, but yeah, also just kind of nice to walk around his hometown. Um, and broadly speaking, Shannon was interested in creative thinking. He gave a talk again in the 1950s that was kind of one of the only times he kind of introspected on how he actually did his cognitive thing, like how he was creative. And he put forth a bunch of ideas and principles for theoretical research. One is simplification, getting rid of detail for intuitive understanding. A second is similarity to a known problem. Third is reformulation. Fourth is generalization. Fifth is structural analysis. And sixth is inversion. And as it turns out, the information lattice actually mathematizes a lot of these principles in certain ways. So the notion of abstraction or simplification is kind of how you get kind of general principles from specific data. Structural analysis is very much present in information lattices as well. You have a hierarchical structure, the lattice structure, and that's how you can break things into pieces and bring them back together and so on. So I found this quite intriguing that, in fact, his own internal mental processes were kind of related to information lattices, though he never made that connection himself. Um, and as I was mentioning, this lattice theory of information goes back to the London Symposium on Information Theory in 1950. I know some of you are based in England, so you might have heard of kind of this being revitalized. I think the sixth or seventh London Symposium was just held this year. But there was a long gap between the first one in 1950 and then the revival. And so you'll notice here, where is it? Yeah, so this lattice theory of information was kind of developed. He presented it in 1950. And then there was a three-page kind of paper that went along with it. But then kind of lay dormant for a long time. And arguably, our work is really the first work in this area in the last, 75 years, let's say. And I think there's a couple of reasons for this. One is he didn't fully explicate it, and secondly, it does require a fairly deep kind of take on group theory and information theory. So my former student and now my colleague Haizi Yu, this was his doctoral work, and now we've been working in a startup company called Kokri that's been really taking it forward. So yeah, he's been really able to take it. Kind of dig deep and really take some new ideas forward. Um, and the other thing I guess it's worth mentioning is, this paper, The Lattice Theory of Information, it has about 200 citations if you look it up on Google Scholar. But about 180 of them are incorrect citations. They were meant to cite the famous 1948 paper rather than this paper. So really, there's only about 20 real citations. So just be careful if you're looking up the lattice theory of information. Okay, so I think we're all living in this era of generative AI right now. It's taken the world by storm. Whether it's what came out in November of 2022 when I was serving at the White House, or ChatGPT or GPT-5, which came out this past week. So I think we're quite used to starting to get used to this. And in some sense, this goes back a little ways. So something I worked on back in 2019 was also a large language model. This was arguably more performant than GPT-2 at the time, and we open weight released it, so it kind of pushed LLMs quite forward and the ecosystem. And this model called Control was the first billion parameter plus model that was openly released. And it also had a kind of a little bit move towards instruction tuning, which has been critical to the chat interface. And so you could have a made up URL as your input, and then it would generate news articles, or there were other methods of prompting that were much more kind of controllable than otherwise. But things are advancing quite a bit. So with scaling, we've seen these kind of emergences, and moreover, we're perhaps seeing plateaus. And so there's a lot of discussion around in the community whether GPT-5 actually is a big advance, or it's kind of just in this plateau region. And it turns out that one can actually prove that under an appropriate information theoretic model, that you'll have these emergences and then plateaus, which we find kind of quite interesting. So this kind of thing is not surprising that you're seeing these kinds of plateaus. And moreover, one can prove the optimality of the chinchilla scaling law for training using these information theory style arguments. Further, one can actually bring inference compute into the picture as well. And so this paper that's going to be appearing in the Transactions of the Royal Society, what we show is that actually sub-chinchilla scaling is optimal once you take inference compute scaling into account as well. And so again, one can think about how to balance compute between training and inference in an optimal way using these information theory style arguments. Okay. But what I wanted to talk about is really this other thing, right? It's very different than LLMs, this information lattice learning idea. And as I wrote with colleagues at Rand Corporation, we think that this could be a different path to AGI, kind of a new way at it. And let me give you a summary first of some of its key properties, and then I'll go back into the mathematical details. So information lattice learning is a white box AI, which is to say, you know exactly what's going on in it. It's directly human controllable, it's human understandable. It requires very little data to train. It's much more compute efficient than neural networks as well. And because we're using very small amounts of data, we can be very easily IP liability free. So for example, an application in music that I'll show you uses just 370 chorales by Johann Sebastian Bach as training data, so which have been public domain for hundreds of years. And then anything you do on top of it is fully traceable and attributable. And so that's the core idea in the company, Kokri, that everyone can monetize their creativity and get credit for it rather than having their creativity stolen and scraped. The technology enables task-agnostic knowledge discovery for scientific, cultural, and various other phenomenology. It's nice, and again, it requires very little data, so you can adapt quickly. And in that sense, we think we're going towards this G in AGI, the general intelligence, the ability to do tasks with very little training. The discovered knowledge is valuable itself, so we've been using ILL for a variety of knowledge discovery tasks, which I'll get into, including in scientific discovery. But it can also be used for downstream tasks like clustering, classification, prediction, semantic compression, creativity, etc. And as I was saying, perhaps a path to AGI that's distinct from the hyperscaling paradigm, because, like I was arguing, we might be plateauing with LLMs. So the way you want to think about it is you can create a foundation lattice. So you start with raw data, you learn the information lattice, and you can use it as kind of a transform. So you have this information lattice transform, and this can be done almost completely domain agnostic, and you learn a concept space. And then you can use it for downstream things. So for classification, and I'll show you this achieves significantly better performance for classification than, say, transformer models. You just use a little bit of a one nearest neighbor classifier or something like that on top of the learned concept space, and you get much better than transformer performance. If you use permutation source codes due to Berger, Jelinek, and Wolf in 1972, again, I believe that was done at Bell Labs when Jack Wolf was there, but I'm forgetting the details. You can get optimal semantic compression. You can actually achieve the rate distortion bound constructively at short block lengths, which is pretty amazing. For creativity, you can decompose and recompose. You can use it for digital twins, et cetera, et cetera. Okay. And the core kind of motivation for us when we were working on this was that when you think about machine learning, the neural network approaches especially are both inscrutable and non-intuitive. So non-intuitiveness is this idea that when models, inscrutability is this idea that when models are available for direct inspection, they might defy understanding. They may be too big, too complicated, and et cetera, for people to get. And the non-intuitiveness is that even when you can understand what's going on, they might rest on statistical relationships that defy human intuition. And most work in interpretable machine learning and AI only addresses inscrutability, but not non-intuitiveness. We wanted to address both. And so what comes out of the information lattice learning are rules that have a direct explanation for why they are what they are. In particular, they correspond typically to group theoretic invariances to symmetries. And so those symmetries are directly human understandable and intuitive as well. Okay. And as I mentioned, we're drawing on these group theory and information theory ideas rather than neural networks. And Shannon himself believed a lot of new ideas in information theory would come from work on complex machines, especially AI, like his Theseus maze following machine. This was arguably the first implementation of reinforcement learning. Okay. And the way we want to do this is we want to first do knowledge discovery, like I was mentioning. Say, for example, take pieces of music, a small number, and learn the laws of music theory, and then use those for, say, composition. And as we do this, we want to learn hierarchies of rules, not just individual rules. And we want those hierarchies to be interpretable as well. For those of you who follow Gary Marcus, he's been talking about the deficiencies of LLMs for a long time, but he also back in 2018 was arguing that there's a need for this hierarchical structure. And so that's what we're aiming for. So for example, if you're learning laws of music theory, you don't want to learn, you want to learn notes and scales and so on and chords, but then you don't want to learn like chord progressions in terms of raw notes anymore. You want to learn them in terms of intermediate knowledge that you have like about chords. So that's a lot like how humans learn things, right? You don't learn the very complicated things in terms of raw notes. You learn them in terms of intermediate knowledge. Okay. And so the basic idea is a little bit like Fourier analysis in that you're taking signals and decomposing them, and then you can resynthesize them. But rather than Fourier coefficients and frequency components, which in music and sound, maybe they're interpretable, but in other fields, for most people, they're not. Here, each of the nodes is corresponding to a symmetry, a group theoretic invariance on which you're projecting, and there's a natural hierarchical structure. And that is what really enables this kind of learning. And moreover, we have this iterative student-teacher architecture as learning. So it produces this hierarchy of symmetry-induced laws. And the interesting thing is, well, first of all, there's this first phase, which is actually solving a difficult computational group theory problem to explicitly construct the lattice structure. And then secondly, you take a little bit of data and do the learning in the lattice. And the output are these rules. And it turns out the same structure, the phase one, this constructing of the information lattice, actually, you can do this for a variety of domains and it works the same. So whether you're trying to learn the laws of music theory or of chemistry or quantum chromodynamics or genetics of neurobiology or all kinds of other things, the same structure seems to work. In particular, particular isometry structure, rigid body transformations, which also correspond to various crystallographic groups and so on. And the kinds of laws, they're kind of related in a way as well. So, like you might notice that all the data, so Tom and Jerry are playing notes on keyboards. All the data is in the top left triangle, you'll notice. And then further, only certain of the columns are covered. And so you can, you get rules like Jerry plays higher notes than Tom, which is a voice crossing rule in music. But you have similar rules in ionic salts. So if you remember your chemistry, the first and seventh columns of the periodic table, I believe, if you mix them together, you get an explosion, but you also get ionic salts, right? So the same kinds of things. Right. And the core idea of the lattice structure is to decompose into partitions. So you might be able to induce different ideas. So like if you partition these shapes, by color, by number of sides, by convexity, those are where the concepts are coming from, right? So the partitioning is how you get concepts. So red and blue, convex, concave, trigon, tetragon, pentagon, and so on. Okay. And this is seems like a very simple idea, but it's actually really powerful. If you go beyond, shapes, you can do this for any alphabet. So you assume you have data that's drawn IID from some distribution P, and the distribution is known. So this is not a density estimation problem. The goal is to estimate, and not to estimate, not to do density estimation, but explanation. So for example, like in music, you might have 4 voices, soprano, alto, tenor, bass, and you want to kind of learn an explanation for the data you see in this space. Okay, and the way, again, like I said, is you do it by partitioning. So x1 and x6 might go together, x3 might be on its own, x2, x4, x5 might go together. And these are concepts, partition cell, and it's a concise way of representing abstraction. And this induces a distribution. When you merge these, you get some probability mass. And so this probability mass, together with the partitioning, is a probabilistic rule. And the kinds of rules you're after are concentrated in probability mass. So, a rule like most birds fly, but that's rare for fish, amphibians, reptiles, and mammals. So you would want to partition these animals into categories. These ones have hair and drink milk, and so on. And so you get cluster A, that's all the ones that have milk and hair, and so on. But then you observe a different property, which is the ability to fly, and you notice it's concentrated in this category C. Bats do fly, and flying fish and so on, and penguins don't fly, but the mass is concentrated here. So it's a useful and memorable rule. Okay. And the way you mathematize this is abstraction as taking the quotient with respect to an equivalence relationship. Given we have limited time for the presentation, I'm going to skip some of the mathematical details. But the core idea, again, comes from the fact that you get refinement of partitions, and this leads naturally to a lattice structure. So red and blue, as well as trigon, tetragon, pentagon, can be refined into red trigons and blue pentagons and so on. And so this already induces a lattice structure. And so, you have this coarse description, everything is all together, and this finer description where things are partitioned much more. There's a huge number of possible partitions, a Bell number, which is super exponential, and that's just the number of nodes, to say nothing of the edges. And it forms this hierarchical structure, this directed acyclic graph of possible concepts. And there's different ways of doing this. You can assert certain features, symmetries from group theory, as I was describing, and you can even start with existing partitions and construct lattices from them. Here, in the group theory setting, you actually can show that the partition lattice is equivalent to the subgroup lattice in the case of finite groups. And so you actually get a lot of mathematical machinery for free. And yeah, like I said, there's a lot of mathematical details in terms of how to compute the lattice structure. You can prove a lot of duality theorems, which help with computation, and all kinds of things. There's some interesting relationships to crystallography, like I was mentioning, and so on. And if you're interested, there's this paper in the SIAM journal on applied algebra and geometry, which I'll point you to. And there's also, like I said, a lot of cool interpretations in terms of Shannon's lattice theory. Shannon actually asserted the probability measures were known. On the other hand, we're saying we're constructing the structure first, and then we're learning the statistics from data. And that's really what goes from the lattice theory to lattice learning, that we're actually doing the learning from data. And a nice way to interpret what's happening as part of this abstraction process, this learning of rules, is the way Shannon introduced it. And so the way he described it was that an information element is an equivalence class of random variables with respect to the same sigma algebra. So, if I say something in English or in Morse code or in French, if they're valid translations of each other, I'm saying the same thing. They're partitioning things in the same way. They're the same sigma algebra, and they should be thought of as informationally equivalent. And that's really the kind of idea of this whole information lattice business, that you're taking things that kind of sound the same, say the same thing, semantically equivalent, and grouping them together. And that's really the core of abstraction or lossy semantic compression. And one can further develop algorithms to learn the laws from data. And the way this works is it's actually fairly simple. You have a student who is going to be as random as possible under the current rule set, which is typically empty when you start. And so, I just press random keys on a keyboard, be as random as possible, maximize entropy, and send that over to the teacher. The teacher listens to my random composition as well as a training corpus like the Bach chorales, and finds the most discriminative rule by maximizing the Kullback-Leibler divergence, and says, here's the most important rule to get you closer to Bach. Now the student is constrained by the first rule, and now is most random under the first rule, sends that over, teacher listens and finds the second rule that's most helpful to the student, and this iterates. And moreover, the teacher is structured according to the lattice, so you don't want things too close to each other in the lattice, and you want them to be concentrated in probability mass. Okay? And so you can go ahead and implement an algorithm like this, and it actually leads to, for example, in music, a lot of laws of music theory. So a simple law that could come out is, as you'll notice, all the probability mass is concentrated on C, D, E, F, G, A, and B, and very little is on the sharp notes. And so if you convert this into language, it's the soprano voice is built on a diatonic scale. A more complicated rule, notice the axis is no longer in terms of the raw notes, but in terms of intermediate knowledge. So individual perfect octaves are favored, etc. And you can have like first year music theory students take the histograms and convert them. I mean, it's easy for them to do, fairly easy. So in a class, we had them as a homework assignment. 3 students got perfect scores, 7 got between a 40 and a 50. 5 students didn't do the assignment, which is always annoying for professors, but that's how it is. But the point is, even freshman music theory students can convert the histograms into words pretty easily. You might wonder, how much knowledge do we actually recover? In fact, what we did was we took the first 3 courses of music theory at the University of Illinois. There's 75 topics that are taught, and 45 of them we recovered directly in the same human-interpretable form as a textbook. 7 are not possible to recover because of the nature of the data. And then of the 23 that are missed, we know exactly why 18 were missed, and we know exactly how to extend the model. It was largely a computational constraint. And 5 were less clear, but and so you're able to recover just on the basis of 370 chorales by Johann Sebastian Bach, about 80% of the music theory curriculum at the University of Illinois, in the same form as a textbook. And you can discover new ideas as well, like the second difference, the acceleration of pitch. Is something that's emerges from our information lattice learning, but it's not really previously considered in music theory. And so we've talked to our music theory colleagues, and they find this quite compelling. And there's much more complicated knowledge that emerges that they find compelling as well, but I won't go into that. And the same thing you can do to learn kind of laws of genetics in neurobiology using single-cell RNA sequencing data. So our colleague from Johns Hopkins, Genevieve, we've been working with her, and we did this just before the pandemic, and now we're revisiting this quite a bit. You can actually learn how genes regulate each other, not just as gene regulatory networks, but actually in temporal patterns, which is compelling. And you can even do stuff for machine vision. So the most basic of tasks, again, I think Jan LeCun did this when he was at Bell Labs, developed the MNIST task. And typically in MNIST, you have 6,000 examples of each digit to train on. What happens if you only have one example? Like literally you just have, this is your training data, just this top row. What would happen? Like using our information lattice approach, you can get around 80% accuracy, whereas a lot of other techniques are, down at 60 or 30%. And then when you get up to 90% accuracy, you can do that with just four examples of our training data, which seems like just kind of minimal, right? Some people cross their sevens and some don't. Some close their fours and some don't. Some loop their twos, etc. Which is really compelling, right? Just with very small amounts of data, you can in the information lattice induced space, you can do really well. Likewise for EMNIST. This is the OmniGlot challenge. And so here you'll notice like convolutional neural nets and so on. We can beat them quite significantly, and we can get to human level performance. And just to note, humans and this Bayesian program learning, they had access to stroke data, like how the 50 different alphabet characters were drawn. Here we're just using the actual final images, so there's some advantage in terms of what's available. Okay. And if you look at quick draw, these are doodles by people of different objects. And here, all these other algorithms are doing pre-training. They're training on a lot of data. We're not doing any pre-training at all. We're in this one and only one-shot setting, and yet we're nearly at human level performance, significantly outperforming vision transformers and all kinds of other algorithms. So again, really compelling that we're able to use the information lattice induced space using very small amounts of data to get really this human level performance. And we're working on a few different applications for knowledge discovery. So one is in super Yang-Mills theory, trying to discover laws in particle physics. We're doing some work in materials, and then also in quantum optics, and hope to have results to report in some of those areas soon. As you may know, Anne and I have been talking about semantic compression as a nice application of information lattices. And as I was briefly mentioning, one can prove that information lattice representation combined with group codes, like permutation source codes, can actually achieve the rate distortion limit for semantic communication for not just the point-to-point setting, but also successive refinement and multiple description settings. So many of the kind of multi-terminal information theory problems in a semantic way can be optimally addressed constructively, not just asymptotically. Constructively, they can be done using information lattices. And just to give you a feel for it, the way you want to think about lossy semantic compression is that you have a piece of music, let's say. So one way to abstract it is to say drop the top line, so sampling. You can abstract away the pitches and only keep the rhythms. You can drop the rhythms and only keep the pitches, et cetera, et cetera. So as you go down the lattice, you're keeping and throwing away various abstractions. And so that's the way you want to think about semantic compression in this kind of optimal way. And then I'll close by talking a little bit about recomposition and decomposition. So you can also do creativity in nice ways, and I think it might be easiest to show you a quick demo, so let me do that. So what you want to do is take, say, music, decompose it into abstractions of rhythm, harmony, melody, and then compose from those. So let me briefly show you uh, um, this existing song. So let me play the song first, and then I'll show you. We call these pieces muons. So these are these abstractions, and then I'll show you how to recombine them. Okay, so that's a full song, but here's one of the melodies that's in it. Hey Jude by the Beatles. This is Bach's Cello Suite. There's this, again, these are not tracks from the song, these are abstractions. So this is the harmonic structure. This is the rhythm. And then when you put it all back together, you get a song like this. Okay, and then you can use that to do all kinds of things, but let me show you just like a creation. So I'm gonna take, I don't know, like say the melody from Happy Birthday, harmony, let me do the same. But let me do a different rhythm. Like this is Mozart's K545 piano sonata. And then, yeah, let me just do piano. Okay, so now I just went down the lattice. So I did these abstractions. So now I have these muons, these pieces, and I'm going to go think of these as constraints, and I'm going to go back up the lattice to get particular realizations of these combinations. Right, so I just clicked it twice. So this would be an example. And this would be another example. Yeah, and just to emphasize the point, this is much more human engaging and human controllable than LLM-based music generation, or I mean LLM style generation in general. Because the human, is much more engaged. We know exactly where the pieces are coming from. We're controlling things, etc. Right? So, kind of a different paradigm for creativity than just text prompting and getting whatever you get. Right? So, I think I'll stop there actually, and then happy to talk more about some of these ideas. Just to summarize, what I showed you was this kind of information theory and group theory approach to AI. So we can learn this knowledge discovery. We can discover laws of, say, music theory or genetics or quantum optics and so on. And then one can use that downstream for a variety of tasks like, say, image classification or semantic compression or various other things. And we think this is really powerful because it's really data efficient. It's really compute efficient. It can run on CPUs. It can run on device. I mean, various things. And it's also very creator focused on the creativity application. So we're quite excited about this. And of course, it's just a bonus that it has very deep theoretical connections to Shannon's lattice theory.